It is now my pleasure to inform you that our first speaker in this morning session is Professor Özgür Müstecaplıoğlu from Koç University. He is also a part of our institute, TÜBİTAK Research Institute for Fundamental Sciences, as a senior researcher. He is going to give a lecture entitled Introduction to Quantum Sensing. Özgür Müstecaplıoğlu received his Bachelor of Science degree in physics as well as his PhD on quantum optics from Bilkent University. His research involves theoretical studies in interdisciplinary areas covering quantum optics, optical properties of semiconductors, foundation of quantum electrodynamics, atomic Bose-Einstein condensate, quantum information science and technology, and nonlinear optics. He is a recipient of Distinguished Young Scientist Award of TÜBİTAK Turkish Academy of Sciences, TBAE, and TÜBİTAK Encouragement Award. With this, I want to invite Professor Özgür Müstecaplıoğlu to the stage to begin his talk.
Thank you so much, Ali Krem Hocam. I hope my voice everything is fine, and my
yes, it's fine.
Fine. Thank you so much. So before I start the technical content, I would like to also express my gratitudes to the supporters of this event, in particular our Ministry of Industry and Technology and our Vice President of Ministry of Industry and Technology, Mehmet Fatih Kaçar, for their presence and continuous support to these events. And of course, I would like to acknowledge gratefully our TÜBİTAK for their continuous support and also for creating awareness and producing excellent students on the topic of quantum technology. So I would like to specifically acknowledge Professor Dr. Hasan Mandal for these efforts. And of course, I would like to thank you, Professor Ali Krem Aliya, for your very hard work and bringing us all together for this very useful event. I look forward to listen all the lectures and contribute my part as well. I'm going to talk about quantum metrology, and I would like to share my screen and whiteboard for this purpose in a moment. So you should be able to see my whiteboard. It should be a yellow grid on your screens. I hope all is fine. I'm going to write here to share the lecture notes, okay? So let's try. So was that visible? I just wrote quantum metrology on the whiteboard.
Yes, we can see that.
Perfect. Okay, so metrology is, of course, very, very old science. It is probably as old as our civilization, right? So in the early years, our challenges were quite simple and local, like we want to produce some growth agriculture, and then we want to distribute this to the citizens of our small society in the ancient years. I'm talking about like 6000 BC. And then, of course, there are famine, and the population for local cultures, they want to grow, and they have to fight against possible famine problems. Then measuring the amount of food produced and distributing it became a serious problem for the development of mankind. Now this can be seen, the efforts to develop means to accurate and precise measurement of the resources can be taken as the birth of the metrology. And it became more challenging nowadays because our challenges are no longer local. We are not only living in a small communities nearby rivers or resources, we are globally sharing resources, and our challenges became, fortunately or unfortunately, at the global level. And as the last pandemic shows, this global challenges requires global solutions. And in this respect, we need more accurate, more precise methods to measure things and develop a standardization over all countries and make a universal definition of methodology as a science. And these efforts, again, can be traced back to industrial revolutions, to the very first one and the first standardization of the measurement system, as nowadays we all use, System International. It was also at the end of the revolution in France, and the meter convention in 1870s became the first effort to make a standardization of the universal dimensions units for metric systems. Now, as a result of recent developments in quantum science and technology, now we have very, very strong and efficient probes, basically quantum probes, to make the measurements. And we will see today that if you use quantum probes, you can beat the fundamental classical limits of measurement and make more precise predictions. So with this basic setup, let me start by some quick definitions that you will hear frequently. Okay, so you will hear frequently in my lecture the terms accuracy and precision, and they play a central role, of course, in methodology. We want to basically improve both of them, especially precision. So precision, in a sense, some uncertainty in the measurement outcomes, and we want to reduce this uncertainty significantly. And as you will see, this is where the quantum technologies help. So let me give a quick example, a standard example to explain visually what are these two terms. I'm making a target. Okay, so our aim is to hit the central point in this target, on this target. So this is a perfect shot, but our other shots can be distributed not as fortunate. Okay, so if you hit the perfect target central point, you say this is 100% accurate. Okay, and if you miss it, then this is less accurate. So you can see that my aim was very bad here, and I made highly inaccurate shots. And at the same time, the distribution of my shots from one another, they're also quite different than each other. And this uncertainty is also high here. So we can say that in this left example, I have very low accuracy. I missed the target significantly. And my misses are also quite highly unrelated to each other, right? So this is also very low precision. Now I can improve my accuracy by hitting the target better, improve my aim, yeah. And then I can also make, of course, a few unlucky shots. In this case, we say that still our accuracy is improved. So I have higher accuracy. I can aim and hit the target better, but still my precision is not perfect. I can still miss and make a distribution of my misses separate from each other. And again, I'm in the low precision limit. Okay. So what we want actually in methodology is to make sure that we have high accuracy. So most of our shots are in the target region. And also we want to improve the precision. So I just wanted to give you some qualitative picture for these two concepts, but we can also make them quantitative because each shot, each trial is an experimental data. When you look at where your aim hits, this is an experimental data. And using this data, you can quantify how precise you were. And for that, we use, probably your students are very familiar with this as well, that there's a standard deviation similar to your grade average calculation. And here we can define these mathematical quantities here. Again, you will hear them frequently in the lecture. There can be different notations, of course, in technical content. And here I will just use sigma for standard deviation, okay? And the standard deviation for some measurement, let's say A, produces some data. It is defined as the difference between the second order moment minus first order moment, or average squared, and we take the square root, okay? So you can understand the logic behind this mathematical definition, because this is simply the square of an output, a single trail, and it is distance to the average, okay? This could be positive or negative error, if you can imagine. And to make them all positive, we just take square of them, okay? Then to get rid of this square at the end, you take also the square root. Okay, so this is the logic behind this equation. And here I just use a simplified notation that this average is the mean value of multiple measurements. So let's say if the measurement distribution is not uniform, then each outcome has a certain probability. This is probability of a measurement outcome. Okay. I is an index of our trials. So if you look at these pictures, I made, let's say on the very left, I made 5 shots. So I have 5 trials. So each of them gives me some output, right? And there's a certain probability of my aim and hitting a certain outcome. And if I multiply it with the outcome, this is the average. If this will be uniform, then you will just divide the outcomes with the number of the trials. Then second moment, this A square. Is defined similarly. You multiply the probability of each outcome with the square of the result of the measurement. Okay. So by this way, you can even define higher order moments, but for standard deviation, only the second moment is sufficient. By the moment I'm talking about this power of the observable A. Okay, so this is important quantity, standard deviation. This is also very common in our everyday life. And it is just the mathematical definition, and the picture shows the qualitative understanding of this concept. Now let's give a simple example. So this time, instead of hitting some target, let's throw a dice as a typical example in probabilistic studies. Okay, so we throw a dice, and whatever written on the top face of the die is just the outcome. Okay, so this is our AI. And let's say we throw it several times and collect some data. But on the average, what I would expect to see. Okay, suppose I make 6 throws. And here, let's say I have 6 throws. So I have 6 trials, 6 times I'm throwing the dice. And look at the outcomes. And here I just multiply the outcome with the probability. Yeah. If this die is perfectly well balanced, if there is no bias, nobody is tampered with the die, then of course every outcome is equally probable. And for a 6-faced dice, I have just 1/6 as the probability. So each outcome can occur at a frequency of 1/6. So if you do this, this is a uniform probability distribution, and therefore, if every outcome is equally probable, I just multiply the possible outcomes. I add the possible outcomes, not multiply, of course, and divide it by the total number of trials, and I'm just going to find here 3.5 as the average result. Okay, this is not written on the, of course, die, but you can expect 3 and 4 are good averages. And the most important for us is the deviation or standard deviation. So we have already average 3.5, and I can put it here. Okay, then I just do this calculation for each possible outcome. Let's say 1 minus the average squared, 2 minus the average squared, and so on. And at the end, the last outcome, 6 minus the average 3.5 squared. I add these results after taking squares and making the addition and divide it by, again, the probability here is uniform. So I just divide this by the number of trials and at the end take the square root. Okay. And if you do this algebra, basically you will find 1.71. Okay. This is a good example to give you an idea how this qualitative picture and formal expressions can be used in practice. Okay. Everything here is, of course, classical. Now, what I'm going to do is I want to now develop an example of quantum mechanical examples. But for this, I want to make sure that we are all on the same footing, and I want to basically very briefly give you some definitions that I want to use from quantum mechanics. And the first very interesting concept is that quantum mechanics has some non-commutative algebraic operations. So historically, when Heisenberg first developed the mathematics of quantum mechanics, he suggested to call quantum mechanics as matrix mechanics. Okay, so measurements in quantum systems, okay, we call them their outputs as observables. Now, this is a very interesting and important concept. Here I was very easily saying that outcomes of my throwing dice are just some numbers. Of course, they're observable and so on. But in quantum mechanics, the observability is a tricky situation. Not everything we can observe in quantum mechanics. And there are also some fundamental limits on to which extent we can observe them. And to appreciate how these observables are different than classical sense, okay, we are going to represent them by some so-called operators. Okay, so if you want to measure, for example, distance, momentum, and so on, yeah, so we just represent them, let's say, by x or momentum by p. Okay, so they become operators, and to distinguish them from their classical outputs, we just put a little bit a different notation, and we put usually a hat on top of them. Okay. Now, the operators have a are different than real numbers, this x and p that you are familiar from classical mechanics, and instead instead of being real numbers, we represent them by matrices. Okay. So what do I mean by matrices and why this is so important? Because if you have two classical numbers like 2 plus 3 and 2 times 3, this classical product is commutative. Product of these classical real numbers are commutative. Okay. So this is why Heisenberg emphasized that quantum mechanics could be called as matrix mechanics, because matrix mechanics differ dramatically from this classical product. That if you have two matrices, let's say A and B are matrices, okay? And in general, if you change the order of the product, you will get a different result, okay? So I can give you a quick exercise that take a matrix like A. You will see this matrix is also quite important in quantum physics. It's a very simple matrix. And let's take one more, a very simple another matrix. Okay, so try to multiply them by changing the order and verify that this product is different when you exchange the order of factors, matrix factors, you will get two different results. Okay. Well, then we are going to make another interesting definition. What's the amount of difference when we change the order in this matrix product? Yeah? So what I mean is, I make this multiplication. I make the multiplication by exchanging the order of the factors. And I just want to take this difference as a measure of the distinction between the two possible ways of multiplying matrices. Okay. So this, instead of writing this in a long way, let's be more economical with our notation. And I'm going to make a definition and call this as commutator of two matrices or two operators, A and B. I will use a shorthand notation, a square bracket. Okay, again, as an exercise, you can take these two matrices I just wrote over there and then calculate the commutator of these two matrices. Okay. Now, the last concept that I'm going to need is the spin operator. Basically, you can treat them without worrying too much about what are they, just three matrices. But let me tell you a little bit physics behind it. Suppose you have a particle, a physical particle. Particle is a funny concept that it has no structure, inner structure. It's a point particle without any dimension, without any internal structure. But we can still assign some attributes to make it interesting. We can, basic attributes are like names and skills of this particle, its capability of doing things. So one thing is that we can say it as a mass. Okay? Maybe we can use it to explain it as gravitational interaction with the other particles. And we can make it even more interesting and say it as a charge by giving another attribute, and charge can be used to define these electrostatic interactions. Okay? Now we can also say that this particle has some kind of rotational degree of freedom, like an internal angular momentum, intrinsic angular momentum. And we are going to call this intrinsic angular momentum as a spin. Okay? We should be a little bit careful that this is not a particle spinning. It has no structure at all. Just some effectively rotational degree of freedom that this particle can enjoy. And this is called spin. So if particles carry spin, to make analogy with the spinning top, a classical famous example that you all learned in elementary physics courses, that you have a spinning top, like a gyroscope. or a famous toy, a historical toy, a wooden conical shape that you tie a rope around it and pull it the string, and then it will start to rotate. So this is a spinning top. So the spin can be somewhat related to this notion. And of course, again, we know that the angular momentum or spin, intrinsic angular momentum, is in this case, it is like parallel to the rotation axis. So we can say that it can be represented like a particle with some angular momentum or spin in certain directions. Okay. All right, so this is just as far as I will go with some very basics of the spin concept. What is important for me that if the spin is observable, if I can measure the spin and represent it like an operator or a matrix, yeah. So you expect that it is going to have some matrix representation. And this is a vector, angular momentum, like objects are vectors. So in general, it has 3 components. Okay, you may align your spinning top in one direction. You can say that other components are 0, but let's be general here. Any direction spin is possible in my case. And these operators, when you make them quantum, okay, with little heads on top of them, we have their matrix representations. And this is exactly the same matrix I gave you in your exercise for the X component. Now, sigma y component of the spin is quite interesting. It is a complex component. I is imaginary number. Okay, this is a weirdness of quantum mechanics, if you like. And this is another matrix, again, I suggested you to try in the non-commutativity example of matrix product. And this is actually the Z component of the spin angular momentum. Okay, so these are very important matrices. They are known as Pauli matrices also. And I wrote here spin 1/2. The reason is that spin also plays a fundamental role in the quantum classification of identical particles. There's a famous Pauli spin statistics theorem. Which simply says that if you have half integer magnitudes of spin for a particle, remember that I assign mass, charge, and spin as attributes to a physical particle. And if the spin magnitude turns out to be a half integer, then these are called fermions. If this is an integer magnitude spin, then this is called a bosonic particle. Okay. So in my case, I will only deal with spin 1/2 systems. The reason is that this is a quantum technology workshop and lecture on quantum methodology, and the spin 1/2 systems, as you can see, they have these 2x2 matrices. The dimensions of these matrices are 2x2. So you can use them to encode 2 bits of information, right? Because they are just 2x2 objects. And then I can assign 2 degrees of information to these matrices, to these spin systems. So it can be imagined like or similar to zero one bit or information degree of freedom. a unit of information. Okay, so from methodological sense, information is also a measurable, and it is a quantity. It's measured in units of bits. And spin 1/2 is a quantum object where you can store information, and therefore it is called quantum bit or qubit. Or there are many different qubits, physical systems, so you can also say this is a spin qubit. Okay, so this is why we have special interest on these spin 1/2 systems. We are not going to deal with spin 1 systems or other objects. So we will be sticking with the only 2 qubits, spin 1/2 systems, and therefore these 3 matrices, simple 2x2 matrices, will be sufficient for the rest of our lecture. Now let's give you your first homework. I will share my email with you. And if you do all of these homeworks or some of them, please feel free to send them to me and we will be in touch. And this is a simple homework, but the results of this homework that I'm going to write here, I will use in the rest of the lecture. As you can see, the commutators of these 3 spin matrices are closed. So you cannot create a new matrix when you calculate these commutators. You will produce each different spin matrices when you calculate the commutators. And I want you to verify this conclusion by doing these calculations explicitly. It's a good exercise to be familiar or even memorize these spin matrices. Okay, this is the first question. In the second part, I want you to look at these 2 matrices. So I'm giving you them as definitions. Okay, this is a definition symbol. It's a combination of the X and the Y components of the spin matrices. These are called ladder operators. Because you will see that at the later part of the lecture that this can cause a flip of the spin. Okay. So we can also say these are spin flip operators. So it can change the alignment of the spin. It can increase or decrease the spin excitations if you like. Again, if you calculate the commutators of them, they form a closed set of relations. But this time I'm not going to give you the results. You can find the results and send them to me. But I'm just giving you a hint that you shouldn't find something different than sigma plus, sigma minus, and sigma z on the right-hand side. This should again be formed a closed set of relations for the ladder operators and the z component of the spin. Okay, so now we are going to make our first important theorem. And relate all these definitions and concepts to our very first objective that I mentioned at the beginning of the lecture, the precision and how these commutators are related to this concept. Okay, so there is a theorem that if you took any courses on quantum physics, this is very familiar to you, but this is called uncertainty relation. So multiplication of standard deviations of 2 operators, A and B, this is always greater than or equal to the commutator on the right-hand side. Okay, this is actually some weak form of uncertainty relation. You could make it more precise by adding anti-commutator, etc. I'm just skipping some technical subtle tricks, but this is good enough for our purposes. And let's immediately find out the result of non-commutativity, the effect of non-commutativity between sigma x and sigma y. Okay, so when you do the homework, you will see that sigma x, sigma y are not commuting, and their commutator is proportional to the z component of the spin. Pardon my notation, but sigma is, if it is sigma x and sigma y, these are spin operators or spin matrices, and the sigma are just the standard deviations, okay? And when they're subscripts or operators, they are standard deviations. So maybe let me change my notation a little bit. So let me use delta instead of sigma. Okay, so just change of notation for clarity. So product of standard deviations are greater than expectation or average of sigma z operator, okay, on the right hand side. So what does this tell us? Okay. So there is always some uncertainty and unprecise measurements when you try to measure x and y components simultaneously. But why do we need to measure x and y components simultaneously? Okay, so in the TÜBİTAK facilities, you may check out to their webpage. There is a wonderful technology called as atom clock. So we can use very tiny quantum objects for very high precision, accurate measurements of the time. And timekeeping is very important, ranging from frequency standards and distributions in fiber optic channels to many other applications. So therefore, time measurements are in modern society are very, very critical. And suppose if this spin of a particle is very similar to our usual clock of or arm of a clock. Okay, so basically, maybe this is an old-fashioned clock, but once upon a time we have these clocks with arms pointing some numbers, right? So let's say this is a quantum particle's spin, and I want to use it to predict or estimate the time. And for this, if this is spin, I just need to have some reference point on my clock, like 12 o'clock. Then separation of the clock arm from 12, measured by some angle theta, okay? And depending on this theta, I can say what's the time. If theta is 90 degrees, I can say time is 3. If theta is 180 degrees, I would say time is 6, okay? So theta will be used to characterize time measurements, okay? And let's say this is a quantum clock, because now spin is a quantum object, it is treated as a quantum clock. But how to measure theta in practice? You can take x component of the spin. Let's say this is our xy frame. And you can take the y component of the spin. Okay. Let's remove this vector now. I have only, it is x and y components. Then this theta is simply arctangent or inverse tangent of sigma x divided by sigma y. Okay. So if this would be classical clock, I would have no trouble. I would find out this angle to arbitrary precision. If I make a small mistake, I can repeat my calculation, and eventually after many calculations, I would say I will perfectly find what time is, okay? But if this is a quantum clock with the spin as it is arm, then you should immediately realize that there is always an uncertainty in the measurements of X and Y. Okay, so this suggests that if the right-hand side is non-zero, the precision cannot be arbitrarily high. Okay, so we cannot measure sigma X and sigma Y for quantum spin objects, operators, simultaneously at arbitrary precision. Okay. Well, then this is, I'm going to show you another peculiar thing. So this is one of the, of course, weirdness of quantum physics, but there could be something even more weird. What happens if I insist to measure sigma X? Okay. So let's look at, let's forget about Y component. So let me just try to measure only the X component. Okay. Now I'm going to say that if I have a matrix, I can find its eigenvalues and eigenvectors, right? It's a 2 by 2 square matrix. You just subtract some parameter X from diagonals, take the determinant, equate it to 0, you will find eigenvalues, and for each eigenvalue, you will find one eigenvector. So let me use a notation for eigenvectors for the sigma z operator or matrix. That is first element in my notation is a reminder. This is the matrix that I'm writing the eigenvalues. And I'm going to denote the two eigenvalues with two plus and minus notations. So I have one eigenvalue sigma z plus and another one sigma z minus. Okay. So remember the eigenvalue problem. You have a matrix. If it acts on an eigenvector, it produces an eigenvalue multiplied by the same vector. Yes. So if I have these formal expressions, this is an eigenvalue problem for plus and minus eigenvalues. Okay. Again, I suggested as an exercise, try to find the eigenvalues and eigenvectors of this simple matrix. Okay, but here it is just a diagonal matrix. So if you don't want to do algebra and if you know this by heart, of course, the first eigenvalue for diagonal matrix will be +1 in this case example, and the other one is -1. And in matrix formalism, these are like 1, 0, 0, 1 column vectors with +1 and -1 eigenvalue. So this is all the diagonalized solved eigenvalue problem, but you can also do this for sigma x. Again, with my notation, eigenvalue of sigma x with the +1, you will find the eigenvalues are again +1 and -1. And in my formal notation, you can also do the linear algebra of this problem and find the eigenvalues and eigenvectors on your own. Okay, so basically, remember sigma x matrix is 0, 1, 1, 0. And here we have some unknown eigenvector in a column vector form. And the eigenvalue is just the ±1. You can find from the determinant, and you can find what is A and B. Okay. So basically these relations are like B is equal to ±1A, A is ±1B. Okay. So from these relations, of course, you can find what is A and B. You need one more condition. This is known as normalization. Because it comes from the Born interpretation of these eigenvectors. So observables of these spin operators, they have eigenvectors with some physical meaning, and probabilistic interpretation of this physical meaning is that this eigenvector is a space is a wave function, and it represents its absolute value square represents the probability, and the probability of all possibilities should be 1. And in this so-called Born interpretation or probabilistic interpretation of quantum mechanics, then we have to normalize wave function so that all events logically gives us the total probability of unit value 1. Okay, so here we have a 2x2 matrix operator of spin with a column vector A and B. This A and B are two possible outcomes of this spin measurement. And if you add their absolute value squares, you are exhausting all possibilities, and therefore these absolute value squares should add up to 1. And if you just substitute these results, relation between A and B into this relation, you will see that A and B can be nothing but one over square root of 2, right? So we can choose, therefore, this way of writing of the eigenvector of the spin operator in the x direction in relation to the spin operators of the z direction and the corresponding eigenvectors. Okay, so when you do the algebra, these are just combinations of this A itself and B itself are combinations of 1, 0 and 0, 1 row vectors. So you can separate them, this eigenvector, in the basis of Z spin eigenvectors. Okay, but this is quite interesting and completely puzzling, because I am plotting usually this spin like a classical vector, right? But this is somewhat misleading, because you cannot say that a vector in the x direction would have components in the z directions, right? So this is completely, again, another example of quantum weirdness. The spin x component and the spin in the z direction their eigenvectors can be expressed in terms of from one another. Okay. Now this gives us the root of fundamental reason why we have these uncertainties, actually, because if you measure the probability of measuring an x spin, x direction spin, let's say with the right direction, okay, and look at the overlap with the spin in the z up direction, and use the Born interpretation to approach it from probabilistic manner, and you will find 1/2. Okay, so what this expression tells us, you have this spin in the x direction, and here you have a spin in the z direction. They are not orthogonal to each other. Okay. So this is a very interesting situation. Even if my clock, let's say, is pointing to 12 o'clock, what if this is a spin, right? And if I just want to measure this angle by measuring the x component of the spin, I might find that actually my clock is pointing in this direction. Okay. And actually I will do this at every 50% chance. At every second measurement, I might find this possibility even. It could be very probable. Or another possibility, that if you also calculate it for the opposite left direction spin in the x-axis, then again, this is another possibility. Even if my clock is pointing 12 o'clock, I will find that sometimes it points 3, sometimes it points 9 o'clock. Okay. So how to make my clock more precise? Well, definitely one fundamental reason why I cannot repeat my measurements and then use the single same spin because there is a collapse of the wave function. But if we make a measurement, it is destroyed. In quantum physics, if you measure the state of the spin of this particle, then it will collapse into the result of the measurement, and you will no longer have a clock pointing 12 o'clock. This is the famous Schrödinger cat experiment. So as long as we don't look at the clock, it can point 3 o'clock, 9 o'clock, 12 o'clock. And when we look at the clock, when we open the box, it will show us possibly the wrong result. Yeah, because if the time is 12 o'clock, it can show us 3 a.m. or 3 p.m. So how to make our clock more precise? We need more measurements, yeah? So for this purpose, we will just make multiple copies of our clocks. And repeat the measurements. For example, 2 measurements. We can find that both of them shows us 3 o'clock. And one measurement can show us, 2 measurements can show us 3 o'clock, or both measurements can also show us 9 o'clock. But sometimes we can measure 1 3 o'clock, 1 9 o'clock, 1 9 o'clock, 1 3 o'clock, okay? But on the average, this gives us 0 because this is spin x in the right direction or 3 o'clock direction. The other one is spin x in the x component of spin is in the 9 o'clock direction. So on the average, their eigenvalues will cancel each other and you will get 0. And here you will have sigma x, measured sigma x is 2, and here it is like -2, okay? So here both in 3 o'clock direction, and here both are 9 o'clock direction, okay? But in the other case, you lose the uncertainty of the single measurement. When you see in one measurement 3 o'clock, you don't know if it is always 3 o'clock. Yeah? If you make one more measurement by using another clock, you will find that sometimes it points right, sometimes it points left, and on the average you will find 0. Okay, so making more measurements. Let's look at the 3 measurements. You can see that again, you make your measurement more certain by this way because unlikely events are becoming less and less possible. Okay, so if you look at these possibilities, then you can see that probability of finding sigma x 0 on the average is now like 1/2 to the 3. Okay, so here probability of finding 0 when you make 2 measurements is like 1/2 to the 2, because out of 4 possible outcomes, 2 of them are always 0. Okay, so by this way you make this probabilities more possible by making more and more measurements, you can increase the odds in favor of the correct result. So this is very similar to binomial coefficients. Okay. The probability of finding 0 here is the most likely event, and therefore it lies in the middle of the binomial distribution. So it is like the Pascal triangle, right? So you have here 3 outcomes, for example, for this case, for the 0 spin or most likely spin average, and then it goes like this. And here we can give you a numerical homework. If you have 25 spins, then what is the probability of possible outcomes of X measurement? And you will find that you will get this binomial distribution, and on average, to a very good accuracy, you will get this 0, and your quantum clock will be more reliable, but still it will not be perfect. Yeah, you still have some finite distribution. Okay. Now, if you do the algebra here, okay, instead of these numerical or qualitative discussions, this 25 spins or n spin state, they're all pointing actually 12 o'clock. They can be written as eigenstates of n spins pointing 12 o'clock. Okay, let's use a shorthand notation. Product of n spins. This is called product state. Okay. So if you calculate the average sigma x for average sigma z for this n spin, okay, you will basically calculate the average of sigma z matrix with these spins. Okay, you will find n over 2. It makes sense because you have, so it will be n. You have n spins pointing in the up direction. This is +1 eigenvalue, so you add them, you get the total spin n on the average. And if I do this for the noise or for the standard deviation, in the x direction, okay, this is basically total spin square. Okay, if you calculate it, you will find that this result is giving you standard deviation for the total spin n over 4. Okay, this is another quick homework for you. So you can see that we have some precision proportional to, or uncertainty proportional to n. And if I want to use, what's the error in angle theta if I measure sigma x? Yeah. then we can use a simple Taylor expansion or basically differential relation that error in sigma x and error in angle we can write such a relation between the errors. This is known as error propagation from one parameter to the other. It's a very simple differential relation. And we can also relate this to our calculation then. Since these standard deviations have square roots, let's take the squares. Okay. And I want only the positive results. So this is my error propagation formula. And if I repeat this experiment sometime, let's say n times, then I can reduce my errors. This is some additional technical remark that you can always reduce the errors by repeating experiments. So you can calculate these results. So here we can have let me show this explicitly. So this is n over 4. Okay. So this is our result here. Yeah. So this is n over 4. And we divide this by m and multiply it by the sigma x derivative with theta. This will be qualitatively easy. In the x direction, if you make an angular change, okay, then this change is proportional to sigma z. Okay, so this derivative is actually, you don't need to calculate this derivative at all. So you can say that this small differential change in x direction, in the angular direction, is proportional to sigma z, and sigma z average was n, right? And this will be 1 over n, okay? So I don't have division by 4 because I just use the problem matrices. I don't divide them by 1/2. So this is just n over 4 there. And this ratio is important. This is known as short noise limit. And the take-home message here is that if you use a product state, then you achieve short noise limit. Okay. This is the upper limit for classical measurements. With the quantum probe in the product state, you can get short noise limit. Okay. So I don't want to go into more technical details, but we can beat this using non-product states or so-called entangled states. Okay. So we don't have time for this, but basically, if you use a superposition of different clock directions, you can beat this short noise limit. So basically, more profound quantum states can help you to achieve classical or even better than classical limits. And that's why we like quantum methodology a lot. Okay. All right. So I think I'm already over my time. So thank you for your patience. If you have any questions, we can, depending on time, and if our moderator allows it, we can discuss. Otherwise, you can email me. And here is my email. Okay, so if you want to do these exercises or if you want to go deeper and see how entangled states can even beat the short noise limit and really squeeze the best of the quantum methodology opportunities, you can contact me. I can suggest you more references and we can chat. Okay, thank you so much.
Özgür Hocam, thank you for this very impressive and nice lecture. Can we now take questions? Can we take questions? Please ask questions.
I already asked a lot of questions, so maybe they are thinking about this. So again, yeah, take your time.
You can also send questions by message using chat box.
If you feel too shy, and feel free to write to me privately and we will discuss.
Okay. As kindly Özgür Hocam emphasized, please write him your questions. Don't be shy. So I will send questions. Can you show me your homework 1 and 2 again?
Which part, Alikram Hocam?
1 on 2. Homework 1 and 2.
This one, okay.
Oh, this one.
Yeah, this plays at the heart of when you do the error propagation calculations. You basically use them to calculate the standard deviation, and then you use it at the numerator of the error propagation formula. And also you have the average of the measurements usually at the denominator, and the ratio gives you some idea about what is the error, fundamental error, due to this fundamental non-commutativity of the observables you are dealing with. And the homework 2 is here. Oh, sorry, this is a numerical homework, right? So you will here calculate the probability of the outcomes of X aligned spin direction for 25 spins, or you can try even larger number of spins if you like, but you will basically develop a shortcut for this calculating this binomial coefficients by looking. So here by hand you can do it for 2, 3, or maybe 4 spin measurements, but for larger number of spins, spin ensembles, and larger number of measurements, it's better to write the code and develop this distribution on your own. Yeah, you can send me your outputs and then verify this observation that if you do more measurements, then still there will be some fundamental with it that you cannot bypass, even if you increase the number of measurements.
But please contact Özgür Hocam, ask him, or send questions, any of your questions to him, as he kindly emphasizes. Now, perhaps at this point we can, some people thank you for this excellent lecture. Yes, of course. So perhaps we can close this section here. Özgür Hocam, what do you think, and start the next?
Of course, thank you very much for participation, and I can share the lecture notes and other things if you ask, okay? Keep in touch.
Okay, thank you. Thank you.